We will cover the basics of the optical flow meter measurement technology in this section. We are seeing a cross-sectional view of the optical flow meter, where the fiber optic sensors are wrapped around the tubing. Each one of these sensors has multiple fiber wraps around the pipe, as seen here, and the sensor array is protected by an outer sleeve so that the sensors are not exposed to the wellbore fluids in the annulus. In its typical use, turbulent flow goes through the flow meter. Turbulent flow contains eddies, sometimes called as pressure fluctuations or vertical structures. And these eddies come in different sizes, from the very small scale to larger scales up to a pipe diameter. As these eddies convect with the flow, they also create sound waves which propagate in both directions, in the direction of the eddy motion and in the opposite direction. Now, the sound may be coming from different sources as well. For example, from the pipe itself or from completion elements such as inflow control valves. In this case, we are interested in the sound waves propagating within the fluid mixture. As these eddies convect with the flow and their sound waves propagate in both directions, they exert a disturbance pressure onto the pipe wall. That disturbance pressure causes a strain, and that strain is picked up by the sensor array, and the eddy motion and the sound wave propagation are tracked by this sensor array using space-time correlation techniques. I'm not going to go into the details of these techniques, but I will describe them in a nutshell. So essentially, the strain signal coming from the sensors are processed in the wave number frequency domain to determine the highest energy distribution of the flow. It turns out that the highest energy of the flow, as depicted here by the red color and the yellow color, the highest energy distribution, it coincides with some inclined lines. And those inclined lines, their slopes, give us the sound speeds and the flow velocity. Now, in the case of sound waves, we have two of these inclined lines because the sound moves in both directions, upwards and downwards. In the case of flow, we only have one slope because the flow is unidirectional. The wellbore fluids are moving towards the wellhead. So let's recap what the flow meter is measuring. There are some direct measurements of the flow meter. Those direct measurements are flow velocity, speed of sound, upwards and downwards, pressure, and temperature. There is also an indirect measurement. We call it the Doppler velocity based on sound speed. Now, the Doppler velocity measurement is rather simple. It's based on the superposition of velocities. Essentially, the sound wave moving in the direction of the flow is faster than the true speed of sound. Why? Because we also have the flow velocity superposed on the true speed of sound. So the family of the sound waves moving with the flow will have a faster velocity than the true speed of sound. Likewise, the other speed of sound, the opposite sound wave family, will be moving opposite to the flow. So the superposition work in a subtractive way, and they will be propagating slower than the true speed of sound. So if we do the calculation, the difference between the sound wave speed moving with the flow and the sound wave moving opposite to the flow, the difference is twice the flow velocity. So by doing a simple subtraction and division, we can find the velocity of the flow solely based on the speed of sound measurement. In fact, this is the way most DAS systems, distributed acoustic sensing systems, measure the flow velocity based on the sound speed. However, this works well with gas-rich flows and gas producers, but it doesn't quite work for the liquid flows due to the high uncertainty of the speed of sound measurement in liquid flows. So why do we need these measurements? Let's actually look at this by going through a two-phase example, oil-water mixture. We need pressure and temperature because we would like to know the density and viscosity of the phases at the location of the flow meter. We need the sound speed measurement, the mixture sound speed measurement by the flow meter to determine the phase fraction, in this case, the water cut for an oil-water mixture. And we need the bulk velocity to determine the total flow rate. We will be calculating the total flow rate by multiplying the velocity with the cross-sectional area. So once we find the water cut and the total flow rate, we can simply find the phase flow rates, oil phase and water phase flow rates with a simple algebra. Now we will talk about this in detail, how we are doing the measurements in the coming sections. So the flow meter at its inline location for this example will be measuring oil and water flow rates. Assume that the flow meter, the pressure at the location of the flow meter is above the bubble point pressure and there is no free gas at the location of the flow meter. So the flow meter for inline conditions will be measuring water and oil flow rates. However, it will also be measuring, reporting standard phase flow rates. And that also means that it will be reporting gas phase flow rates as well. Because as we all know, as the oil moves towards wellhead, the pressure will be decreased and the dissolved gas in the oil phase will be released. So on the surface, we expect to see a gas phase as well. So the two-phase flow meter, while it is reporting only oil and water flow rates for inline conditions, it will also be reporting oil, water, and gas phase flow rates for the surface standard conditions. So in a way, even though it's a two-phase flow meter, it will be reporting three-phase flow rates on the surface. So we can actually see that as a pseudo three-phase measurement. We can also directly measure a three-phase flow. So the flow meter can sit in a three-phase flow and the three-phase flow measurement is possible. We can do this in two different ways, by either measuring the density by means of a secondary PT gauge or a water cut measurement by means of a water cut meter. That way, using that third information, either density or water cut, we can determine the three-phase flow rates. We will talk about this three-phase measurements in the coming sections. Now, in terms of performance, the flow meter for single-phase flows provides a better performance than ±1%. And for multi-phase flows, the performance is around plus minus 5%, which is very good for multi-phase flow meters. Now, in this section, we covered the main measurements of the flow meter, how we are doing those measurements, and why we need those measurements to determine the phase flow rates. We will go a little deeper in the coming sections.